Welcome to this explainer. Today we're going to take a bit of a step back. We're stepping away from all that heavy academic jargon and, honestly, the rigid memorization you might be used to in chemistry. Instead, we're looking at the fundamental building blocks of our material world. So let's just dive right into a straightforward, genuinely practical guide to sorting polymers. So, have you ever actually stopped to notice how a simple, everyday object, like, say, a clear plastic water bottle, and the very DNA residing inside your own cells, share a hidden fundamental connection? I mean, it sounds kind of like science fiction, right? Linking our human biology so closely to synthetic objects. But there is this beautiful underlying architecture connecting them both. Hold on to that curiosity for a second, because we're going to explore how nature and human engineering use the exact same structural secret. Section 1. The invisible world around us. To really understand the materials we interact with every single day, we first have to look at their physical structure. And it all comes down to one core idea. Everything in this category is made of tiny, repeating building blocks. Now, I know the word polymers sounds intensely scientific, but its Greek origins are actually remarkably simple. Poly just means many, and mer means units. So a polymer is literally just a large molecule made of many repeating units. A single unit? That's called a monomer. Think of a monomer as a single metal link. The polymer? Well, that's the long, interconnected chain you create when you snap hundreds of those links together. It really is that straightforward. When you try to visualize a macromolecule, you might picture what looks like a highly complex, honestly intimidating three-dimensional web. But here's the secret. This massive structure is just the exact same simple monomer unit repeating over and over and over again. Once you recognize that single building block, the entire architecture suddenly makes perfect logical sense. Section 2. Origin, nature, or lab. So how do we actually begin to sort these things? Well, we can neatly divide them into two origins, natural and synthetic. And it's pretty fascinating to realize that nature was absolutely the original master engineer here. Long before humans ever had laboratories, nature was building natural polymers. We're talking about the DNA in your body, the starch in your potatoes, the cellulose in plants, and the proteins in your muscles. On the flip side, the synthetic stuff is the result of human engineers basically observing nature's brilliant chain link design and then learning to mimic it in the lab. That's how we get everyday materials like Teflon, PVC, and bakelite. But modern science is beautifully blurring the line between these two origins. Take a synthetic polymer called polylactic acid, or PLA. While it is technically synthesized by humans, it's actually derived from renewable, naturally occurring resources, like cornstarch or sugarcane. We literally ferment natural sugars into lactic acid and then link them together in the lab to create a biodegradable material that helps protect the earth. It's just a perfect harmony of natural source and synthetic assembly. Section 3. Heat, melt, or set. Another great way to organize the material world is by looking at how it reacts to warmth. We sort them into two specific behaviors, thermoplastics and thermosetting polymers. Honestly, the easiest way to understand this is through a simple kitchen analogy. Think of thermoplastics kind of like a stick of butter. They're made of long, linear chains. When you apply heat, they soften up, and you can reshape them. When they cool, they harden again. You can melt and remelt butter all day long. But thermosetting polymers, they're more like baking a loaf of bread. They form a highly cross-linked, three-dimensional network. Once you bake that bread, once it is totally set, you can never unbake it back into dough. Applying more heat will eventually just burn it, not melt it. If we picture the chemical structures for things like polyethylene and polyvinyl chloride, or PVC for short, we don't need to get bogged down by the exact letters or bonds. Instead, just imagine their overall shapes. They form long, straight, linear chains. Because they're organized in simple rows with fairly weak forces between the distinct chains, they can easily slide past one another when warmed up. That simple linear shape is exactly what allows thermoplastics to gently soften and melt. Section 4. Monomers. Twins or teams. Okay, our third classification looks at the actual composition of the chain links themselves. We divide these into homopolymers and copolymers. And this is incredibly straightforward. Just ask yourself, is the long chain made up entirely of identical twins, or is it a diverse team working together? If every single link in the chain is exactly the same monomer unit, like pure polyethylene, it's a homopolymer. But if the chain is derived from two or more different types of monomer units working together to provide unique, combined strengths, we call it a copolymer. So it's really just the difference between a solo act and a collaborative team. Section 5. Polymers with superpowers. Now, you might be wondering, why does this sorting matter outside of a college textbook? Well, when we actually understand the structure, we can harness what I like to call polymers with superpowers. For example, PMMA, which is an acrylic, has such brilliant glass-like transparency, it's used for optical lenses. Teflon has an electronegative structure that gives it extreme heat and chemical resistance, which makes it absolutely perfect for nonstick cooking and industrial seals. We even have extrinsic conducting polymers that can actually carry an electrical charge, opening doors for advanced data storage and LEDs. And perhaps most fascinating of all, we have smart materials. These are polymers and alloys that dynamically respond to their environment. And these smart materials, they literally have a life-saving potential. Consider a medical vascular stent used to open a blocked artery. Because they're made from shape memory materials, they can be compressed down to easily travel through a narrow blood vessel. Then, triggered simply by the natural heat of the human body, they seamlessly remember and expand right back to their original, wider shape, normalizing blood flow. It's incredible. Understanding polymer behavior at a structural level is literally saving lives. Section 6. A teasful final thought. The absolutely crucial point here is that categorizing the physical world is not about rigid memorization. You do not need to memorize every single chemical bond. Instead, these simple frameworks we talked about, natural versus synthetic, melt versus set, twins versus teams, they're just logical tools. They give us a clear, calm way to interpret the complex material world around us. I'm going to leave you with this thought. By understanding the links of the past, from our own DNA to lab-created wonders, we can thoughtfully build a more sustainable future. When we really know how materials are put together, we know how to recycle them, we know how to synthesize biodegradable alternatives like PLA, and we know how to heal the human body. Thanks so much for joining me on this explainer. The next time you pick up a basic household object, take a look at it and ask yourself, what invisible repeating chains are secretly holding your world together?